Okay.
Okay. So, yeah, so I really want to talk about the Grothendieck Teichmuller theory of Gaussian designs today, but I've been somehow, I guess I'm blaming you for this, that you got me interested in this high school geometry of acute triangles. And I just still can't resist saying one more thing about it before we quit, and how it relates to elliptic curves. And to try to keep this little prelude from taking over the discussion, I'll try to frame this in the form of a puzzle. And the puzzle is sort of, I don't get it. Can somebody explain it to me or something like that? So let me tell you, I mean, right, I've been claiming that acute triangles and elliptic curves over the complex numbers are almost the same thing, sort of. We're drawing pictures to support that idea. But let me try to make it a little bit more explicit. Some of this is a little bit more explicit. A way to start with an acute triangle and get an elliptic curve from it. I mean, I guess we already know a way like that. In other words, right? I guess the way is you take the acute triangle, you double it, you know, you sort of glue it to its own copy to make a parallelogram. And once you got the parallelogram, you get the elliptic curve from that in the usual way. That's a fundamental domain for rolling up the complex line or whatever you call it.
And that doesn't matter which way you double it. There are like 3 ways in general to double it, right? But I guess they all give you the same lattice.
I guess that's right, and that's probably, and you're probably describing some way that 3-bang fits into the modular group or something like that, or the extended modular group or something like that. What? Say it again?
Yeah, so that's one way. Okay, so what's another way?
Well, first let's observe something that's maybe unspectacular about that first way, which is that it's of course a transcendental function. See, and the puzzle is going to be, I'm going to describe the second way in a way that I can't see where the transcendentalness is creeping in. So you're supposed to eventually figure out for me, teach me where the transcendentalness is creeping in the second approach, which I'm about to describe. So you ready?
Yep.
Okay. So, oh, I guess I should have stolen screen here. I don't know how I do this. Share screen. Okay, so my little notebook is visible there. Okay, but you're not so visible now. Okay, so we've got an acute triangle. Let me make it a darker color. That's supposed to be an acute triangle. And boy, this is going to sound a lot like the first way, but there's something that's different. Let's see. So how is this? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. I guess it's over there. Something like that. Well, okay, yeah. I'm giving up on drawing these correctly. So this is just freehand. Okay. So I am going to so this larger triangle is just really the same triangle, but just kind of scaled up and turned upside down, and scaled up by a factor of 2 in length, which means factor of 4 in area.
Mhm.
And well, just kind of fold this up into a tetrahedron. And it works. Uh-huh.
Yep, that's like your old, I associate it with you, this idea.
Yeah.
of versus quincunxial and all sorts of stuff like that.
Yeah, yeah. And can you see the point where the apex will land up? I mean, the point on this plane, the point on this graph paper over which the apex of the tetrahedron will lie. Can you give like a verbal description of that?
It's one of the 5,000 different centers of the.
Exactly. Exactly. So it's the, can I say which one it is?
I should.
Yeah, no, you could write. If you don't try to come up with the official name for it, you can just describe what kind of, how you get it. I mean, just fold these up, you can kind of see. So let's see, you're folding this one up, so what happens to it? I guess it ends up kind of like this one on the bottom here. If it, am I saying this right? What does it do? It ends up like that or something like that.
Whoa.
You know what I mean? I mean, it's like.
Well, when you fold it all the way over, it ends up there. I thought, but yeah, okay. But I thought you were going to fold it up to a three-dimensional object, so that. I thought you were asking me which way the maybe, yeah.
Yeah, no, I'm saying that no matter how far you fold it.
Oh, I see. It's on that line. Oh,
it's on that line.
It looks like you drew a really scary one here. Because that's.
Yeah. Oh,
well, because you have to find the intersection of three such lines now.
Right.
And it looks like it's got to be way far into the southwest corner of that original triangle, which is.
Yeah. It's a slightly exotic center of the original triangle, but it's a perfectly ordinary center of the larger triangle.
Oh yeah, sorry, I'm getting. That's right. I don't know what it's called. I don't know.
Well, for the larger triangle, it's the orthocenter, the intersection of the altitudes.
But it's the intersection of these three types of dashed lines that you.
Yes,
drew.
that dashed line is called an altitude of the larger triangle, of the doubled triangle.
Oh, okay. Sorry. I was mixing up altitudes with the lines.
I hope I am getting the terminology correct, but I think this is called an altitude.
Yeah, you're right. Yep. Thinking badly. Yep. Okay, that's cool.
Yeah, so it always lies, right? For an acute triangle, this thing is always going to lie in the unscary region of the big one, but it's just sometimes in the scary region of the.
So it can lie outside the small one?
Yeah.
I
have a feeling this one does, but I'm not even sure.
Yeah, you certainly made it. Yeah. You said I'm drawing one myself. It looks like it's really easy to have that happen. Yep.
Yeah. So, I like I say, I've been getting distracted by all sorts of questions. Like,
I see. Yeah.
When does this apex lie over the small triangle? When is it sort of an acute tetrahedron? When does this give you an acute tetrahedron in some sense, this sense of acute tetrahedron from an acute triangle? No reason in the world I should be obsessing over those questions, but I keep on having trouble putting them aside. But and so I've been reading up about all sorts of fascinating stuff about orthocenters, which sounds like it's related to this. I should try to put all that aside. I just want to state the puzzle here, and then we put this aside. So, all right, we've got this tetrahedron now.
Yep.
And this is not a regular tetrahedron, no more than the original triangle was a regular triangle.
Yep.
But it has some symmetry. It has this,
True.
what?
True. Sorry. True.
Yeah, because we've, created from 4 copies of the same acute triangle. So, I mean, and the amount of symmetry it has this Klein 4 symmetry. The Klein 4 of the, I call it the Ferrari-Klein subgroup of 4 bang, because Ferrari used it to solve the quartic. But it's this, it's the subgroup of disjoint pairs of transpositions or something. Those, those.
Huh?
So that's like a what? A normal subgroup of the alternating subgroup or something like that. I don't know, whatever. But it's got this symmetry, this limited symmetry. And that limited symmetry, that's also the same symmetry as the symmetry of the cross ratio function. For 4 points on a, right? If you have 4 points on the projective line, whether it's the real projective line or the complex projective line, you get this cross ratio function from it. It's coming from the sharp triple transitivity of the Möbius transformation group, or the linear fractional transformation group, or whatever you call it. And so you can get this cross ratio thing from 4 points in order. But what happens if you rearrange the order? Well, you have 24 ways to rearrange the order, but they don't all give you different things. They don't all give you different numbers. They don't all give, that's not 24 different functions. It's only 6 different functions, because it has this Klein 4 symmetry. So what I'm kind of claiming here is, if you think about that symmetry property of the cross ratio function, that's saying that, am I saying this right? Yeah, every spherical tetrahedron, and whether you picture it as, made out of triangles, curved triangles living on the sphere, or if you think of it as this spherical, as this tetrahedron inscribed inside the sphere, right? You can get back and forth between those two. You've got this well, I guess I'm saying that conformally, every tetrahedron, every spherical tetrahedron conformally has this Ferrari-Klein symmetry, because cross ratio has that symmetry. So, but clearly they're not all metrically Ferrari-Klein. They don't, a random tetrahedron doesn't have the Ferrari-Klein symmetry metrically. It only has it conformally.
Does this type of tetrahedron here give you, in some functorial way, a spherical tetrahedron?
Well, I mean, it's the same thing like with an acute triangle. There's the so-called, again, I happen to know this because I've been reading up on acute triangles. There's this thing called the circumcircle of an acute triangle. And it's really, maybe is it the orthocenter? It's some center. It's just, right, there's this thing.
But you just circumscribe the triangle in a circle.
Yeah, I mean, but it has to do with, finding the center of that circle is the thing that's equidistant from all 3 corners or something like that.
Right, okay.
And it's straightforward. So you can have a circumsphere of a tetrahedron.
Right, if it's not too weird of a tetrahedron,
So you can have a circumsphere of a tetrahedron. And
okay, so that's how you do it. That's a way to do it. You might think of other ways.
Right. So like I was saying, every spherical tetrahedron is conformally Ferrari-Klein, but not metrically Ferrari-Klein. But these ones are metrically Ferrari-Klein.
Right.
So these are like, the perhaps good canonical representatives of these orbits under the Möbius group of the the Möbius, the conformal group, whatever you call it, acts on the spherical tetrahedrons. And so there are these orbits, but there are these metric representatives where the Ferrari-Klein symmetry, which in general is only conformal, actually becomes a metric thing. So I think this is like a unique representative of each orbit. I hope I'm not screwing that up. And
it's cool how you got from some moduli space of triangles to some kind of moduli space of tetrahedra.
Yeah, yeah, and I think it's also cool the way you then take the circumsphere and think of that as a Riemann sphere, and so you now have got these 4 branch points on the Riemann sphere, so that you can take double cover, and or
yeah, that's great. So what's the quiz question? Just to get.
Well, I already stated the quiz question. What am I doing here that's transcendental? It almost seems like I'm just doing high school geometry. Everything is algebraic. I mean, I think I almost see. I think I do see, where I'm making my stupid mistake. Because I think, I thought about this a couple of years ago, and I can't remember how unconfused I got myself about this, but now I almost think, right, there is a subtle transcendentalness in here. But does that puzzle work at all for you? Do you get confused for a moment? It's because let me finish making it sound like it's. Let me finish making a specific modular function sound like it's not transcendental. So the specific modular function that I have in mind is this level 2 one, this basic level 2 one, the cross ratio. Right, we've talked about that before. In fact, when we were talking about this quincunxal stuff and everything, in this week's finds, you mentioned this modular function, the cross ratio. So you have to go to level 2. You need a labeling of the 2 torsion points, these 4 branch points, and at that point, you've successfully broken the symmetry, the 4-bang symmetry between the 4 things, and you can just take the cross ratio. So that's a modular function, a level 2 modular function. And I guess, right, another way to think about it, right, is, there are these cubic polynomials, and normally you can't tell the roots apart or something like that. But when you go to level 2, the roots become identifiable, not just the coefficients, but the roots become identifiable. This has something to do with 3-bang instead of 4-bang, because I don't know, it has something to do with this 24 versus 6 versus 4 or something like that. But so you can also just think of this modular function as your favorite root of the cubic polynomial. And normally you can't talk about a favorite because they're all interchangeable. But here we've broken the symmetry enough at level 2. They actually have a favorite root of the cubic polynomial.
So that sounds very algebraic.
Yeah, this all sounds very algebraic to me. I've never, this morning I was, thinking I don't know the answer to this, but now I'm thinking I sort of do know the answer to this, but I'm trying to make it sound like I don't know the answer to it. So, but I'm not even sure. So, right, you start with this acute triangle, you just fold it, you make these 4 copies of it, and you fold them up into a tetrahedron. This all sounds like high school geometry. The circumsphere, that's all high school geometry. And then, you just got the course ratio. Course ratio is an algebraic function. So what's going on?
I don't know. You've managed.
All right. Let's put that aside.
Okay. So then next week you can give away the answer.
Yeah, and there could be a number of answers. there could be some answers that say, oh, we just made a stupid mistake. There could be other answers that say, hey, there's actually something interesting going on here. And I'm not sure which kind of answer will predominate. But I'm sort of hoping that I did sort of successfully put you in the same state of confusion as I was.
Yep.
And in fact, I even got rid of some of the confusion, I think, as I was giving it to you. But
yeah, to skillfully fool someone into thinking something wrong about mathematics, you have to understand it very well. So, yeah.
Right. But it's like conservation of confusion or something like that.
Right.
Okay. So
okay, I will manfully resist asking to know the answer right away.
Okay. Yeah, because I think it's good to think about. Well, you know, but it could also be related to that. You know, I talked about the acute triangle and this coordinate functions for the moduli stack of acute triangles. And we had these like barycentric coordinates when you used the Beltrami Klein projection. I'm wondering whether it's secretly related to that in some way. So that's another, you know, this puzzle that I just introduced, it really is connected to earlier stuff we were talking about acute triangles, or it may be connected. These are all things you could, you know, if you want to go down a rabbit hole, like I did, you can distract yourself with all this stuff. But now, so now I'm trying to successfully, right? So I'm blaming you for taking out into this big digression about the high school geometry of acute triangles when I was trying to tell you about the Grothendieck Dyke theory of Gaussian designs, the design and font or whatever. But the Gaussian ones specifically related to the Jugendtraum. So, right, so I had that big digression in my research, that big distraction, and I was, you know, I was worried would I be able to get back to this topic and understand it again? And I think I got you worried about that too. But I think I'm now actually back in the mood to understand the Gaussian design. So I'm trying to go now talk about Gaussian designs. And oh right, and I sort of want to encourage you that it's not that bad. I think the second time I'm coming in, I think I'm understanding things better. So, you know, maybe the vacation from thinking about this, maybe it actually helped me. Maybe it can help you too. You know, maybe I can explain it to you better now. So what am I trying to say? So let me try to draw these examples again. It's probably easier to just draw them again than to look in the notebook and find them, because I'm not skillful at finding them in the notebook. So does that look like the right one? There's that parallelogram, which looks very nice and rectangular. There's this other one, which looks like what does it look like? It's supposed to be the same area as that one. So maybe it's like that, and that, and that. Those look the same area to you? I think this is probably the correct parallelogram.
I don't know, maybe, yeah, whatever.
I mean, theoretically, we could just use Pick's theorem, right? But okay, so right, we're dealing with this Gaussian group, the affine general linear group in one dimension over the Gaussian integers. And the Kronecker diagram for that has a kind of reflection symmetry. So when I color, yeah, let me just draw that again. So what does it look like? It looks like the Kronecker diagram. That's the Kronecker diagram. So Yeah, so if you have meta red-green color blindness, like you can tell the difference between them, you just can't tell which is which or something like that, then you could get confused, or I don't know whether that's good or bad or something like that. But I guess I was just trying to give an excuse for why I constantly forget whether I should be using green or red or something like that. So, and it's because what? It's because, like, you could, I think what I usually do is I think of the reds as the Gaussian integers. I think that's a good convention. And the greens as the deep holes for the Voronoi tiling. And but for the Gaussian integers, unlike for the Eisenstein integers, it's really hard to tell the difference between the Gaussian integers themselves and the deep holes, because they're both just the same kind of lattice. So
what's the Coxeter group here? You said it's like GL Gaussian integers? No.
I think I said AGL
Right. Okay.
1 over the Gaussian integers.
Okay.
I hope I'm getting that right.
Right. Okay. Yeah. Yep, that sounds right.
Right. So I think it's like, let's see, I guess the red is the Gaussian integers themselves, or you can think of them as the Voronoi cells. Yes, I think the reds are supposed to be the Voronoi cells, which are associated to the Gaussian integers. And the greens are supposed to be the deep holes, which are the vertexes between the Voronoi cells. Yeah. And then the blues in the middle are the edges of the Voronoi cells or something like that. But this was all, I just brought this up to give myself an excuse for, I can't remember whether I should, whether I should put the reds in the corners or the greens in the corners. So maybe I'll put the reds, I'm going to put them in the corners here, I guess.
The toughest decisions to make are the ones that have no effect at all.
Exactly. I mean, you shouldn't have said that, because there's theorems about that.
I know. That's your whole shtick about Galois theory. Yeah.
Well, but okay, I guess everything is Galois theory, but I'm thinking of another theorem. Well, I guess you're right. I guess it is Galois. But it's something like, well, maybe it's just, I don't know, by definition, something is, in order for something to be a legitimate function, it has to be like a natural transformation, but that means that you can make it unique if you force your hand enough or something like that. Sorry, I shouldn't even get into that right now. I'm just drawing in the dots, and I'm also thinking that right, it's like uniqueness implies naturalness, but naturalness also sort of sneakily implies uniqueness if you cheat a little bit. Implies uniqueness or something. Okay, so I'm just trying to draw in the tiling, the design. These are the two designs that are supposed to be in the same Grothendieck-Teichmüller orbit. And what does it look like? Boy, that was bad. Try to pretend that I drew this correctly. Doing this right? And what does this one look like? So there's an annoying thing in the way I drew the this second one. I'm using this black color. I'm doing this right.
You're using it both for the boundary of the shape and also for this other.
Yeah, I should have made the boundary a different color or something like that.
Yeah.
Is this the way it goes? Yes.
Looks. There are a few vertical ones. I don't know if you want to draw two vertical, yeah, and it's mirror image.
It's mirror image where?
There, right there. Okay, maybe it's not a mirror. It's some kind of a mirror.
But there's a missing one, you're saying?
Oh, never mind. Now you got it. Sorry, I didn't see it. Okay.
Okay. Yeah. So right. So I have a conjecture based on the Jugendtraum that these are actually in the same Grothendieck Dyke-Miller orbit, which I think I sort of know what it means to be in the same Grothendieck Dyke-Miller orbit. But I want to actually prove in this example that whether or not these really are in the same Grothendieck Dyke-Miller orbit. And I keep on vacillating back and forth a bit between whether it's obvious or whether it's false. Whether it's obvious or whether it's obvious or whether it's not obvious. I mean, I think it's true, but I'm not at all sure that it's true. So I vacillate back and forth between, how much work do I really need to do here? But so okay, so I have some idea. Oh, well, let's see. So right, one of the tricks that we already came up with was that we want to convert this into a genus. These are elliptic curves, so these are genus 1 examples. But if we just mod out by, if we think of these elliptic curves, so they're groups, and with a so there is something. Oh, so
yeah, I was just gonna say, yeah, I know it's while you're busy talking, I'm staring at this thing. Yep, I noticed it. Yeah. Okay.
Did we screw up? Did I screw up anywhere else? Okay. If you catch any other ones where I screwed up, let me know. Right, these are genus 1 things. These are elliptic curves, so they're abelian groups. So we can, just christen a base point, and I guess I want to christen a base point as a red thing. I guess I think the convention will work out better if it's a red thing. And well, but then we're actually interested in all of the 4 because I want to get something genus 0 from this, and the way you get genus 0 thing is by identifying each element with its inverse in the abelian group structure. And that means that all the 2 torsion points get identified with themselves. So those 4 2 torsion points are becoming the 4 branch points of this covering map from this wrapping covering map from the genus 1 thing down to the genus 0 thing. And so right, you can easily see where those 4 branch points are in the left-hand example, right? It's like there and there, there and there. So again, every time I use the yellow highlighter, it makes the blue things look green, but try to remember that they're actually blue. So I mean, it looks like there's a red and a green and 2 blues. And I think the same thing should be true here. So where are the 4 two torsion points over here? So it's like there. Do you know where the other ones are? I guess, yeah, I guess it's just right. It's just like that. And so for the second one, it's also, I'm hoping it's also true that it's a red and a green and 2 blues. Let me take away the yellow so I can count the colors better. It look like, yeah, a red and a green and 2 blues. And then the other one, it's also a red and a green and 2 blues. But on the other hand, they're sort of arranged differently, right? But I'm hoping, well, were you going to say something?
No.
I'm hoping it's not just a coincidence that you know, they both share this property of having a red and a green and 2 blues for the 2 torsion points. Because I think that's something we need if these are really in the same Grothendieck Dyke mode orbit, I think. Anyway, so you get the genus 0 thing by modding out by that, modding out by, you know, inverse in the group. You know, thinking of one of these corners as your, oh, well, I guess for both of these parallelograms, the corner is all just 1 point, right? Because in the design, right? So where we're using the corner points as the identity element, the base point, and we're identifying things with their inverse. So so how does that work? I think it's something like yeah, so it's like, right, it's the 180-degree rotation. Well, right. So somehow, right, you can also think, right, there's some elementary thing that's making it clear that you could also just think of it as 180-degree rotation around the green thing in the middle instead of around the red thing. And I guess, yeah, so maybe it's easier to, yeah, you can take any of the 2 torsion points and you can call that the base point. So let's see, the center on the left is green, the center on the right is actually blue. Is that right?
Yep.
But that's okay, because we're just using this to get how the, you know, that's not something that, you know, because we're just using sort of arbitrary fundamental domains that break the symmetry. So it shouldn't bother us too much that the one on the right has a blue center and the one on the left has a green center. But I'm hoping you can see that well, I guess we could use that as a sort of symmetry. So it's, yeah, it's 180-degree rotation around these mid diagonals or whatever is the thing we're modding out by to get the genus 0 thing. And I'm doing this right. I want to say something like, you know, you can picture it like that and like this and like that and like this. And we have one of those things, one of those little things we were drawing in the first part of the discussion when we were doing the puzzle. So this is just a thing that you can fold up to get a tetrahedron.
Oh, cool. Mhm.
And that is this genus 0 thing. That's this Riemann sphere with the 4 branch points on it. And so where would it be on this second one? It would be there. How does it go? Why is this so hard to draw? Okay, so we want a triangle that's just like that. So maybe it goes like that. This. Yeah. So for each of these, you fold each of these up into a tetrahedron. Each of these little purple things. I hope you can see that they're purple.
Yep.
And so again, I was a little bit worried that even though they're distinct at the genus 1 level, I was afraid that when you wrap them up like this into genus 0 things, that they might annoyingly become equivalent. But no, they're still inequivalent. And like we had like little, well, we're gonna work out the combinatorics of this. We're gonna try to work out the combinatorics of this in more detail and try to get the.
So they're inequivalent what's? So they're like, it sounds like they're like, you're getting genus 0 curves over the Gaussian numbers or something like that.
That's right, but they have these designs on them. So they're, all Riemann spheres are equivalent to each other, but they have different designs on them. These designs are these, little things with green and red and blue vertexes and then black edges between them.
So if I could fold up one of those tetrahedrons and mentally keep track of all those damn colored dots and edges between them.
Yes.
Be combinatorially distinct.
Yes.
I hope you do that sometime.
Well, I think we've actually done it already. But so maybe we'll refer back to that, or maybe we really want to do that.
Okay.
And if I was better organized, I'd have all this together and we'd see what you just asked about, and you'd see it right here. But we may have to redraw it again or something like that. But so this is a context where we're trying to understand what Baez theorem is about. So once we get it down to the genus 0 examples. So that means we've got these, these designs are really just pictures of meromorphic functions, where again, there's a convention here. It's like the greens are infinity. No, yeah, maybe I don't know. Maybe our convention is the greens are 0, the blues are infinity, and the reds are 1. And then the black edges are the unit interval. And, so these designs are little pictures of these Belyi functions, or whatever they're called. These, functions that are involved in Belyi's theorem. So, what's the key property of these Belyi functions? Just to remind ourselves, it's something like their critical. Yeah, their only critical values are infinity, 0, and 1. If the function has a critical point, then the value of the function at that point has to be infinity or 0 or 1. And the combinatorics of the little design is really telling us everything about that in a way that we can reconstruct the whole meromorphic function. And the meromorphic function on the Riemann sphere, if it were on a higher genus thing, then it would be some sort of, algebraic function. But here it's just a rational function. And yeah, so one of the things we're trying to do is we're trying to write down like a system of equations for well, I think the original way I was originally thinking about it was a system of equations for figuring out the coefficients of this Belyi function. How does it have coefficients? Well, it's a rational function, so you can give it a numerator and a denominator or something like that. But okay, so one of the things I've learned is that it seems better to try to not focus so much on the coefficients of the Belyi function, coefficients in any sense, but just focus on the locations of the green and red and blue vertexes. Because you can kind of more or less completely reconstruct the Belyi rational function from those locations. So what am I trying to say? So let's take, well, right, we're gonna have to do the combinatorics in some detail here, but some of the things that are easy to see here is that, relatively easy to see here, if you stare what's going on here, you can see that there's really just two green vertexes on this genus 0 thing in both of these cases. Can you kind of see that? Like over on the left is kind of this one and this one. Those are the only two things on that genus 0 surface. There are only two greens on that genus 0 surface. And there's only two reds. Is that true? Why is that so confusing? Yes. Okay. That was a little bit confusing to me, but you know, there's the one that's at all the corners.
Right.
All right, there's a little bit of purple edge that's missing there. Okay, so right, there's the reds at the corners, those are all the same point. And then there are these two reds over here, but those are also the same as each other, right? When you fold it up, those become the same point, those two reds right there.
Yep.
So there's just two reds. And if you count it up, there's 4 blues. And that's maybe it always goes like that. Maybe there's always the same number of greens and same number of reds, and just double that in the number of blues, because that's, you know, kind of general trend of this Gaussian thing, you know, coming from the Coxeter group. And so what am I trying to say? Well, so there's this, you know, we're going to be dealing with rational functions, but rational functions are made out of polynomial functions. So let's take a polynomial function. I'll call it G for green. So the green polynomial function is going to look like something like G of Z equals Z. How does this work? Z minus, you know, I may have to pick better variable names at some point, but for the moment I'll just call it Z minus A, Z minus B. Z and Z are the same thing. And one of these should be to the 4th power. One should be to the 2nd power. Because if you look on this, if you look at the, I mean, maybe this picture should be twice as big so you can see it better or something like that. But
yeah, it's pretty hard to see, but I guess I'm supposed to count like the number of black lines coming out of it?
Yeah. So I'm hoping it's,
the idea is clear. I can't.
Right. Or I always forget, are you supposed to divide by 2? It's, yeah, the idea is clear. That's right. The idea is clear, but the picture is not clear. So it's something like that. And the one for the red, you know, R of Z is Z minus, I guess I'll call it, I guess I'll call it E. And yeah, and that's, yeah. I mean, so this is also like that, but we just need different variable names, E and F, for these red things. So A and B are the names of the green vertexes. E and F are the names. Oh, that was stupid. Let me call them C and D instead, because we're going to need 4 of them for the blues. So C and D isn't enough for the blues. So it's okay. Sorry. Okay, and the one for the blues, there's going to be 4 blues, so it's going to be something like I'll call them H, J, K, and L. So there's like, am I doing this right? I guess. Okay, so we've got, what am I trying to say? We've got green and blue and red vertexes. And for the green ones, we call them what? A and B. For the red ones, we call them C and D. For the blue ones, we call them, what do we call them? H and J and K and L. And yeah, and under this Galois symmetry, this Grothendieck-Teichmüller symmetry or whatever, the ones with the higher exponents do really stick out like a sore thumb. I mean, those are the ones that are like 2 torsion points. So let me try to, maybe circle where the 2 torsion points are. So those are the 2 torsion points. And the other ones are the ones that the other ones are the ones that are not 2 torsion points. I mean, I guess they're all like 4 torsion points or something like that. Is that what I'm claiming? That doesn't sound right. Maybe there's 6 torsion points or something like that. So, I mean, I think it's going to end up that the A and H and J and C are just going to be rational, because these 2 torsion points on like, the Gaussian elliptic curve, I think they're going to be very fixed under this Galois symmetry, whereas I think right, okay, what am I talking about here? I'm talking about the fact, right, the Galois symmetry switches back and forth between this elliptic curve and this other elliptic curve. The alleged Galois.
Okay, that's what you're claiming, yeah.
Yeah. So I think I'm claiming that, these four torsion points are going to have, sorry, 4 2 torsion points. Those are going to have, at the genus 0 level, right? Or even, yeah, I mean, right, yeah, because right, the branch points are the points that don't branch, so I think they still remain rational. Well, so right, I mean, I had sort of stupidly forgotten or something, right? Part of the whole point of this example, when I tried to work it out, was that this should be a really simple example. This should, the whole Galois symmetry should just be quadratic. And, and I knew that because we just had, it's supposed to switch back and forth between these two elliptic curves, these two Gaussian designs. But somehow I was stupidly not realizing that that should mean that, that B and K and L and D should just, it seems like they're just going to be quadratic irrationals. Whereas H, J, and C will be rationals. That's what I think. That's what I think. And, these will all be 6 torsion points on the Gaussian elliptic curve, or something like that. And yeah, so the Jugendtraum is telling us all about how these torsion points on the elliptic curve are in the same orbit under the absolute Galois group of the Gaussian integers, or of the Gaussian field. So I'm just trying to prepare us for, just trying to anticipate that hopefully this algebra that we're going to be doing, which I'm not quite sure how far we're going to get with it today, but we'll get as far as we can, that it's going to be, we may go through some messy stuff, but it should be just heading towards something very simple, just involving quadratic equations, quadratic irrationals. And it should be right. It should be the same. This should be the same quadratic irrationals that you deal with when you're working out the 6 torsion, or mostly just the 3 torsion of the Gaussian elliptic curve. That's what I think is going on here. The same quadratic irrationals that you deal with when you're working out the 3 torsion of the Gaussian elliptic curve should be the same thing that's showing up here in the Grothendieck-Teichmüller theory, Grothendieck-Teichmüller action relating these 2 Gaussian designs. So yeah, just trying to give us propaganda for the idea that this should actually work out very straightforwardly as we go ahead. We shouldn't get too scared of things here. So so you can do things like you can get a rational function by taking G over B or something like that. Well, let's see which one would make the most sense in terms of the way I had it set up. I think I wanted it to be green is 0, blue is infinity, and red is 1. So it seems like I should take green over red, I guess. Is that right? So like this is going to be, this function is going to be the Bellier function, this function that's supposed to, right? I've already arranged that that this rational function will have its zeros at the green vertexes, and it will have its poles at, oh, no, so you're telling me I did screw it up. So it was correct the first time. It should have been blue. Is that right? Just because, right? I want it to be 0, infinity, and 1. So blue is the infinity, green is the 0. So yeah, I apparently had it right the first time, I think. So this particular rational function should be the Bellier function that we'll use. But if you permute, right, there's 6 ways. Go ahead.
What happened to the reds or the 1s? Why doesn't it? matter.
Yeah, well, I mean, you know, we're supposed to be writing down a system of equations, the solutions of which give us the Beltrami function, and we just haven't finished writing down all the constraints yet. But I've already sort of eliminated a whole bunch of stuff here by writing it in this way. I mean, okay, so what do we call this? Let's call this, can I call it F? This rational function F. This is going to be our Beltrami function. And that tells us some constraints that G and B and R should satisfy. So right, I mean, so I'm right. So, you know, like I say, there are these 20, well, are we still connected?
I'm back.
Okay.
Yeah.
But how much did you miss? Just a fraction of a second?
Yeah, not much. I'm still confused about why this F doesn't care about R.
No, it does. It's just that we haven't written down those constraints yet. You know, the constraints about how it behaves at the green vertexes and the constraints about how it behaves at the blue vertexes are already built in. You know, I didn't even have to write down those constraints because I wrote the form, you know, the form in which I wrote G and B as polynomials automatically makes it that, you know, the zeros of this F are at the green vertexes, A and B. And the form in which I wrote B makes it so that the poles of F, if I get it correct,
because this F here is like a completely oh, I see. So you don't know. Okay, so never mind. What? So you don't know what A, B, C, and D, whatever. You don't know what all these guys
that's
are.
right. Those are the right. So so we have what? We have 8 variables here: A and B, and C and D, and H and J and K and L. And those are the 8 variables for the system of equations that we're trying to write down. So I used to have other variables that were the coefficients of these polynomials, but I've already eliminated those coefficients because, right, you just take the you just multiply out these polynomials. You just get their coefficients.
Right.
And now there's maybe like one little glitch in here, which is that maybe I need one more variable or something for the right. I mean, when you know where the zeros of a polynomial are, you can still right. There's the question of whether the polynomial is monic or not. I mean, right. The way I've got it arranged here, G and B and R are monic polynomials, but maybe I'll have to say something like that, that maybe it'll work out that instead of the, maybe the values of F at the red vertexes, maybe they'll end up being, instead of being 1, maybe they'll end up being some other constant, K, not K, but M or something like that. So, you know what I'm saying? Yeah, M for multiplier or something. It's sort of like a Lagrange multiplier or something like that. I might need one more variable in the system. I'm not sure I will need it, but I might need one more variable in the system, which I'll probably call M or something like that. But it's just this multiplier variable M will just be a kind of fudge factor to address the issue of whether these polynomials have to be monic or something like that. I'm being very sloppy about that because I didn't completely clear that up in my mind yet. But mostly, right. Mostly there's going to be 8 variables in this system of equations. And it's, the locations of these vertexes, locations of the green, blue, and red vertexes. So there's 8 of them. Right, but hopefully the system is eventually supposed to work out to be quadratic. We're going to, try and write down all the constraints we can think of. So yeah, so right, we've got f of z, and yeah, maybe I should think of that as like right. There's also like f of let's call it. Well, let's think of f itself. Sorry, let me write this. G f of GBR is just defined to be f. But if I do it in some other order, if it's like let's say GRB, for example, then this one is defined to be I guess it would be G of Z over RZ. So I mean, right, there's these 6 different rational functions that we can cook up from these 3 polynomials. With these 3 polynomials, from that we can cook up these 6 rational functions, and those 6 rational functions are supposed to be related to each other, right? Those are constraints that we can write down, right? That like if you do 1 over 1 minus x to f, then you should get some other permutation or something like that, because 1 over 1 minus x just permutes infinity and 0 and 1. I think it permutes them cyclically or something like that. So right, so I'm not at this point. I'm not trying to write down all these constraints in an efficient, syzygy-less way. I'm trying to more write them down in a conceptual way. So right, so see what I'm trying. I'm doing better. What I'm trying to do is say that associated to the green vertexes, there's this Young diagram, which is, what is it? It's like, am I doing it right? Is it this one? And associated to these, let's see, associated to the blue one, it should be this Young diagram like this. And associated to the red one, it would be, I guess, the same as the green one. And I have no idea why it is that the blue one is sideways, the green and red one. So I have no idea about that. But sideways or something like that. So yeah, this is green. Sorry, I'm having my own color blindness problems here. First one was supposed to be green. I was trying to draw green there.
I have to go away for a second. Let me just pause.
Okay.
I think I can pause the recording.
That's fine.
Yeah, I'll be right back.
Okay, so we're back now. So yeah, I'm trying to say that you can think. Right, I'm trying to give a conceptual idea, and we may have mentioned this before, but I'm trying to say that the geometric conceptual interpretation of this system of equations that we're writing down is that we're intersecting 3 varieties in some space. So what am I trying to say? So there are these, like, a Young diagram gives you a sort of, let's say the Young diagram is called D. so associated to a Young diagram D, there's this D diagonal subvariety, which is simply, where the variables, these 8 variables, obey, I shouldn't say these 8 variables, it's some 8 variables. No, I'm sorry, it's 6 variables. What are these 6 variables? It's okay, I'll have to think about what conceptually these 6 variables are. But from the Young diagram, right, each Young diagram has 6 boxes here. So we're getting these partitions of 6 into some parts. And associated to such a Young diagram, there's this diagonal subvariety where, instead of being 6 variables, it just ends up, for the green one, instead of being 6 variables, it ends up just being 2 variables, because 4 of them have been set equal and 2 of them have been set equal. So, right, I mean, this corresponds to the, what were you saying?
Yeah.
I mean, right, the generic fibers of this Belyi function are just going to be 6 element discrete sets, the generic fibers. But then there are these special fibers. There's the special fiber over 0, which is supposed to have this, be shaped like this Young diagram. It's just supposed to be 2 values, but one of them is, sort of weight 4, and the other one is weight 2. And the fiber over infinity is more like this blue Young diagram. That is, there's 4 separate ones, but 2 of them are double heavy and 2 of them are single heavy, et cetera, et cetera. So, and what we're doing when we're trying to constrain this system of points, we're trying to constrain this system of vertexes to be the locations of the infinities, the poles, the zeros, and the ones, the zeros, the poles, and the ones of this function. What we're secretly, conceptually, geometrically doing there is we are intersecting these Young diagonal subvarieties. That's what the system of equations that we're trying to get here is. And, so the intersection of these Young diagonal subvarieties should be this dimension 0 thing that we're trying to get at here. Right, this system of equations that we're trying to write down here is, right, I mean, we're trying to remember stuff that we did a while ago, but right. Where, ultimately there may be some very subtle constraints that we have to put in that really know some detailed information about the combinatorial structure of the diagram. But to begin with, just to get it down to a dimension 0 intersection, where all we're doing is we're just putting in separate information about the greens, separate information about the blues, and separate information about the reds. So if, I call it the vertex censuses. It's just, keeping track of the degree of each green vertex, the degree of each blue vertex, the degree of each red vertex. That's very far from being a full set of combinatorial invariants for this planar graph, right? It's really, I think it's really just telling you kind of something like I'm not saying this quite right, but it's more like it's giving you the non-planar structure. So right, these, not a planar graph has a lot more structure than just a non-planar graph. And so we're not even, we're not even putting in the full combinatorial information that we have about these planar graphs or these planar designs. I should call them planar designs at the moment. But we are putting in enough information. Just the information about each color separately is enough information to get it down to a zero-dimensional subvariety.
So in terms of a graph, I thought you're just saying, you're giving me the information about the degrees of each red, green, and blue vertex. Is that all you're getting? Is that enough? That sounds like less than the information in a non-planar graph. It must be mixed up somehow. If you think that, is it because we know extra stuff besides those degrees?
Let me think. Oh boy, let's see. Yeah, that does sound like this, because which green, I mean, sorry, there's a whole bunch of things I'm being very sloppy about here, partly because we're beginning to run out of time here. But like, right, there's a number of different, one of the things I should say out loud here, instead of sweeping under the rug, is that there's a number of different combinatorial tricks that you can play with these designs. There's a way you can just look at you can erase the blue vertexes, just look at the red and green ones. And that's, if you do it in the right way, that's enough information to reconstruct the whole graph. I mean, you put in the, right, you just put in the reds and the greens and the edges from the greens to the reds. And then in that case, the blues can be recovered. You don't need to explicitly give the blues, because you just recover them as they correspond to these regions. Each blue occupies a region that's bounded by these green edges that go from the green to red things here. So there's a whole bunch of tricks that you can play here. One of which involves just erasing the blue things, which just leaves you with a bipartite graph between the green and red. And then, yeah, so you just asked a really good question, and I'm sort of panicking because we're running out of time. So I'm not going to give you a really good answer to your question right now. But
that's okay.
But that's the kind of thing, that's very much the kind of question that we need to straighten out to actually do this. But at the moment, since we're running out of time here, I'm just trying to give us a sense of where we're going here. So, I'm saying that this manipulation, these algebraic manipulations that I'm doing over here involving, the form in which I wrote the polynomial G, that was taken from this Young diagram. And it's, has to do with the fact that there's this Young diagonal subvariety for the green stuff. There's this other Young diagonal subvariety for the blue stuff. There's this other Young diagonal subvariety for the red stuff. We're trying to intersect those together, and that should give us a zero-dimensional thing, which means that the fact that we're getting a zero-dimensional intersection means that we're making at that point a lot of progress. By that point, we will have made a lot of progress in writing down the constraints that we need, and then we can just haggle over the remaining constraints in order to try to understand the subtleties of the Grothendieck-Teichmuller action and the Grothendieck-Teichmuller orbits and stuff like that.
So I don't know why you think you're getting, you're getting down to a zero-dimensional thing from that. Maybe once I knew.
Right. We did talk about this, and it's like some, numerological minor miracle. You can work that out. Maybe we should work that out. We have worked it out before, but see, okay. The last time we did this, we were probably cheating because we were probably in the case where there was a unique blue vertex. In the case where you have a unique blue vertex, you think of the blue vertex as the infinity value. And I mean, you know what I mean? At that point, you've got a rational function that just has a single pole of some multiplicity. But a rational function that just has a single pole, you can reinterpret that as a polynomial function by thinking it's taking infinity to infinity. So the last time we made progress on this kind of algebra, we were probably doing that special case where you just have a unique blue vertex, and that means you end up with these polynomials. So I guess maybe the way the terminology works is that in that case, the Belyi meromorphic function reduces to a Shabbat polynomial. And then you can just, work with the coefficients of the polynomial and stuff like that. But here, these Gaussian designs, we have to face up to the fact that, they have a lot of vertexes of each of the three colors. So we're not dealing with polynomials. Our meromorphic functions really are, even in this genus 0 case, they really are rational functions. And, so instead of just having a single polynomial, I'm sort of stuck working with three polynomials, and the ratio between any two of them gives us a rational function. And then, these 6 rational functions are related to each other in some way, and we may have a multiplier variable for fixing the glitch that I didn't fix. And so this is the kind of situation we're in here. And yeah, so right, I guess since we are running out of time, this is kind of just anticipation of when we actually work this out. So I'm saying that when we actually work this out, this should be not that bad to work out. It sounds like there's a lot of variables, 8 variables. But right, so one of the things that we have done mostly, except for this little glitch about the multiplier variable, is that we've mostly eliminated a whole bunch of the coefficients that were extra variables in our system of equations. Those extra variables were the coefficients of some polynomials or some rational functions or something like that. And those have been eliminated just by writing these polynomials in this form that comes from the Young diagrams. And yeah, so we've actually reduced, it could have been worse. We could have had, 25 variables or something like that. I may have had 25 variables the last time I tried this. But I've now got it. This is a big success now that it's just down to 8 variables with possibly a 9th helper variable. And then, yeah, so then we when we flesh out this whole system, it should factor into some, this whole system should decompose, it should have geometric summands. So the polynomials should factor or something like that. And it should all just factor into quadratic things, I think. Yeah, because of whether the Grothendieck Teichmuller orbits should be, this should just be a 2-element Grothendieck Teichmuller orbit. So I think all the algebra is going to, if I didn't screw up, it's all going to, when we factor this into things, the factors or the main factor that we're interested in is just going to be like a quadratic factor or something like that, like a quadratic factor of this system. That's going to be reflecting the quadratic Galois symmetry of this Grothendieck Teichmuller action. And this quadratic nature should be the same quadratic nature that you get when you study the 3 torsion of the points on the 3 torsion of the points on the Gaussian elliptic curve. Yeah, and I think that's going to make sense. Right, so what is the Gaussian elliptic curve? It's something like y squared equals x cubed minus 1 or something like that. I mean, there's different ways you can write it, but that's one way to write it or something like that. So what is it? It's like the places where the derivative of x is 0. Those are the branch points, the 4 branch points, but the places where the derivative of y is 0. 0 or infinity or something like that. Those are going to be the, I think that's going to be like the 3 torsion or something like that. So it's going to be like x. I'm just, you know, groping for computational facts here, but I think this is the way I think we're going to get things not to work out nicely when we actually do this. So we're going to have to work out the combinatorics of these diagrams and write down the systems of equations and everything. But is there anything I'm forgetting to say before we quit here? Since, you know, we're not actually going to do the computations right now, but I'm just trying to say that what we're going to do when we have time next time. So I hope you're getting some sense of what we're going to do. And I'm hoping that this was not a bad reintroduction. Like you say, it's been a while since we've talked about this, but I think I'm actually understanding it better now. And I'm hoping that when you see us start to really do concrete calculations with this system, that it will reacclimate you to the ideas even better. But is there anything we should do before we quit here? There must be all such things I'm forgetting to say here, but
Yeah.
Is there anything that's
No,
really,
I think
anything really annoying you
we'll
about
need
it
to
at the moment? What?
Oh, what's annoying me is that we like spent 2 weeks on this other thing, and I've been forgetting everything that I knew about this stuff. So, but I mean, that other stuff was great fun. But now all sorts of things I feel like I don't remember as well. So anyway.
Yeah, but I think it's gonna get better as we jump into this. I think it's gonna get better. You know, I was totally annoyed at myself for having forgotten all this stuff. But as soon as I jumped back into it, I really got back to it. And I think there are good things happening here. So I'm hoping that I'll be able to reacclimate you to it as soon as we really jump in and do this. I think this will be a good example to work out, and this will really help us understand the general theory, the general conceptual ideas that are going on. And I think there's all sorts of interesting ideas going on here. And again, you know, this is the attempt to connect the Jugendtraum to Grothendieck's that font or whatever it's called. So I mean, you know, the ancient ideas of the Jugendtraum, we're trying to put them in this modernish context of Grothendieck's ideas. And there's that little quote that you found of Tate or somebody saying something about you know, something about Grothendieck disclaimed any knowledge of the Jugendtraum, but you found a quote that said that Tate told Grothendieck one time that he had reinvented the Jugendtraum. And
right, somebody, maybe Tate, had done so. So
yeah, so that's what I'm hoping we're kind of learning here, that we're learning what Tate was really talking about. But anyway, we're kind of out of time here. So thanks a lot.
Okie doke.
Okay.
See you next time. Yeah.
Okay. Bye.
Bye.